Welcome back, ladies and gentlemen, to your favorite class, AP Statistics. Today I'm going to go over problem set 13.1. Topic is the chi-square test for goodness of fit. Side note, most students find this to be one of the easiest, if not the easiest, lessons and chapters of second semester. Part of it might be because you have some familiarity with chi-square if you've done AP Bio, and part of it is the calculation's a little simpler. So let's take a look here. All right, first problem here, a fair die. The die is tossed 200 times, normal six-sided die, and here are the results. So these are our observed counts. Is there reason to believe that the die is loaded? That's a term we use for we have an unfair die, a die that isn't weighted equally. By the way, if you go in the casino and you watch the craps table, from time to time you will see them take a die and they'll hold it on this balancing device, and they'll spin it and just check. If it wobbles, then they go up. It's not weighted evenly, so they'll remove that from play. So they check their dice all the time to try to prevent any cheating, any biased results. Okay, so here we go. Chi-square goodness of fit test. Null hypothesis. The die is fair. In other words, all sides are equally likely. Okay. Alternative. The die is not fair. Okay, meaning one or more sides is more likely. Okay, now the chi-square test, basically what we have to do is calculate our expected counts, right? We have the observed counts, and so the expected counts are, if I throw this thing 200 times and I expect each of the six sides to come up equally, that means my expected counts are all actually 200 times 1/6, right? I like to make a table personally, so I'm going to do the observed and the expected. Okay. All right, so for the number 1, we observed 26. For 2, 36. For 3, we got 39. For 4, we got 30. For 5, 38. And for 6, we got 31. Okay, so there's my observed counts. Now my expected are all the same, 200 over 6. Okay. So the idea here is this is what we would expect to see on average, right? We can't actually get 200 over 6. That's not a whole number, right? It has to be actually a whole number. But that's the thing. This is what we would expect on average of doing this many, many times. So we're asking ourselves, did what we observe, was it close to that, or was it so far away from what we expected that we're going to conclude the die is loaded, right? The die isn't fair. And that's how a chi-square test works. Okay, in order to have a chi-square distribution, all of our expected counts have to be, for our book, at least 1, and no more than 20% below 5. Okay, some books just say all at least 5. A little simpler, but that's not what our book does. Our book has a little more tolerance for potential error. Ooh. So anyway, all these are at least 1, and 0% of them are less than 5. So all expected. Misspelled expected up there. Oh well. All expected counts are at least 1, and 0% are less than 5, so it is safe to proceed chi-square calculation. And by the way, this is called a chi-square goodness of fit test. Okay. Lesson 13.2 will cover another chi-square test, the chi-square test for a two-way table, right? This is a goodness of fit. We just kind of have one row of observed and then a row of expected, or one column of each. Next time we'll do it for a two-way table, so we'll have multiple rows and columns. Okay, so to calculate our chi-square statistic, okay, it's on our formula sheet, bottom of the first page. We take the observed count for each cell minus the expected count for that cell, square it. We divide it by the expected count, and then we take the sum of all those. Okay, so on this problem, it would be 26 minus 200 over 6 squared plus 36 minus 200 over 6 squared. Oh, since they all have the same expected count, I was just going to write one big common denominator. But a lot of times the expected counts can be different, so I don't want to confuse you. I'll do that on each one. Right. And you keep going until you do the last one. And there we go. Okay. And this is the work, because obviously you're actually going to end up doing it in your calculator. Okay. All right. So I already entered these into my lists. Now, some of the older calculators, the 83, for example, I don't think it has a goodness of fit calculation, but it's not hard with lists. So I'm going to do it with lists first, and then I'll do it with the goodness of fit choice. So all I got to do is find the difference of those. So let's see, list 1 minus list 2. And you can just, enter that right now, or if you wanted to, you could put even more in there and say list 1 minus list 2 quantity squared. And if you want to put in more, go ahead and say divided by list 2, and now you got the whole thing, right? Okay, so I just plugged in that formula right there minus the summation, right? So now I just have to do the sum of list 3, and I've got my chi-square. So let's see, list, math, sum of list 3. And there we go. So this is 3.94. Okay, so that's how you can do it. If you don't have the feature, it really isn't that hard. You just enter the formula into an empty list. If you do have the feature, right, go to Stat, go over to Test, and towards the bottom, you'll see two choices. The chi-square test, that's for a two-way table. That's not what we're doing right now. And the chi-square goodness of fit test. Please, if you don't have the goodness of fit test, don't try to use the two-way table. It's not going to work. The degree of freedom will basically be an error. You'll see why when we do lesson 13.2. So if you have this, go for it. And if not, just do it the way I showed you with your lists. It's not hard. Okay, so list 1, list 2. The degree of freedom. Okay, so we have n minus 1 degrees of freedom. But n is not 200 when I do a chi-square. It's not the sample size. It's the number of categories. Okay, so we have 6 categories here. So our degree of freedom would be 5, right? Because there were 6 sides to our die. And there you go. You can see we get the same 3.94 that we got. And there's our p-value. Okay, so p-value is 0.558. And there you go. Now, sometimes we'll say, hey, how about read your table instead of use your calculator? So here's how we do it. Flip through your packet until you find table C, the chi-square table. Go to degree of freedom of 5, read across, and you'll see, hey, 3.94 is off the left of the chart, meaning your p-value is greater than 0.25. So using the table, that's as accurate as I could do here. But that's accurate enough. At this point in time, you should all realize a p-value that's above 0.25 is a lack of evidence. Okay, but there's the more accurate, a lack of evidence. So conclusion, with a p-value of 0.558, we have a lack of evidence I'll say, how about this? Because a lot of you like to talk about the null hypothesis, so to reject the null hypothesis. Now, once I say that, I'm not done. I need the context, right? So we have no evidence that the die is loaded. All right, now I've written an answer that makes sense to someone who doesn't know statistics. Okay, so just want to point that out because some of you still like to just write about the null hypothesis, and there's nothing wrong with that. It's just you at some point have to talk about what does this mean in context of the problem, right? Somebody who doesn't understand statistics should be able to read the conclusion and go, oh, okay, the die isn't loaded, right? All right, let's try our next problem. Okay, Trix cereal. All right, we've got 5 fruit flavors. Each flavor has a different shape. Blah, blah, blah. Ooh, spends a lot of time. Wow, that took forever to do a whole box of cereal. All right, test the null hypothesis. The flavors are uniformly distributed versus alternative they are not. So in other words, again, all flavors are equally likely, just like our die. So I'm going to, again, make a quick little table and write my hypothesis. All flavors are equally likely. Alternative, not all flavors are equally likely. Okay. Let me point this out. I will sometimes see students do something like, well, I don't want to show you something that's wrong, so I'm not even going to go there. But realize, always write it in words, okay? Because sometimes students say, not equal, not equal, not equal, not equal for every category. And that's not the case. We're saying at least one category is different, okay? Not that every category is different. We'll accept anything that shows a difference. All right, observed counts, expected counts. Grape is 530, 470, 420, 610, 585. Okay, they didn't tell me the total. No, all right, so not a big deal. We'll put these counts into our list. Okay, and now to get my expected, I need the total, but hey, we have a feature for that, right? I just did it. Go to list, math, sum of list 1. So that's 2615. All right, that's my sum. So list 2, if they're all equally likely and I have 1, 2, 3, 4, 5, it's 2615 over 5. Oops. Sorry about that. I wasn't in the body of the table. Here we are. 2615 over 5. So, okay. And this is common to have that as your alternative, that they're all equally likely, or not all equally likely, and your null to be equally likely. That's common. But sometimes, as you'll see in a problem coming up, sometimes we'll say, oh, 10% here, 20% there, right? It won't always be a uniform hypothesis. All right, so these are all 523. And again, our work, we take our observed count. Oh, actually, before I do the work, or check. Okay, all expected counts are at least 1 and 0% are less than 5. So, a chi-square goodness of fit test should be safe. All right. Now, the calculation, we take our observed count minus our expected count, square it, divide it by the expected. And do that for all 5 flavors. I wrote a plus there. Fix that. And it's a minus. Okay. And now again, if you're using your TI-83, you basically just enter the formula into list 3. So the observed count minus the expected count, square it, divided by the expected count, and find the sum of list 3. Whoa, that's a biggie. But then again, we have much larger counts, so we'll see what happens here. Okay. Oh, but not that many categories. So yeah, this is going to be highly, unless I misentered something. Let me double check. Oh, looks like I entered everything right. So yeah, this is going to have a very small p-value, be highly significant. Okay. And again, if you have the goodness of fit test, you can do that. Degree of freedom here is 4. Highly significant result, right? P-value 1 point whatever times 10 to the negative 9th. Okay, so our conclusion is the flavors are not uniformly distributed, right? We have very strong evidence to conclude that. Very strong or extremely strong evidence. And there we go. Another chi-square goodness of fit. All right, so hopefully these are pretty easy. Let's keep rolling. And yes, here's the one I actually just spent quite a bit of time getting ready. The M&M problem. This is something you may have done in AP Bio. It's a very common use of the chi-square test. And it's fun, you know, get some candy and count. Too bad we don't do this around Halloween time when everybody's got the Halloween candy laying around. But anyway, M&Ms are supposedly in this ratio. Let's see, the peanuts here, peanut butter and almond. Oh my gosh, I bought a bag of plain and counted it up. Doggone it. All right, well, let's just pretend. Let's pretend that my candies are peanut M&Ms. I wish I would have bought peanut M&Ms. I actually like those better. Darn. Should have read the problem before I went to the store. All right, so anyway, we'll just pretend, because the important thing is doing the calculation. All right, so I bought a bag of M&Ms. without checking which type of M&Ms. Yay, big old family-sized bag. And then I spent forever counting them. And I got, see it was fun, 175 green, 167 orange, so on and so forth. So got them all separated. So let's make our table. So null hypothesis is, I guess we'll pretend they're peanut ones. So 20% brown, yellow, red, and blue. 10% green and orange. Yeah, we're not gonna match that because orange is a really big count on mine. I already can see we're gonna get a small p-value. But hey, that's all that matters. We'll do the calculation, right? And then it does not follow the claimed distribution. Okay. All right, let's put the observed and expected. Oh goodness, I forgot to do the informal follow-up on our last problem. Let me jump back and finish that real quick. So I forgot to point out, whenever you find a significant result, you should go back and say, where were we off, right? Where did I find something that really didn't follow what we were claiming? So that is one of the reasons why you really do want to do it with your list, because you can see on the Trix, that first category was pretty much in line with what we were expecting, right? The second category wasn't too far off. It was this third category was way off, and then the fourth category was off by quite a bit as well. So on the Trix problem, the follow-up should be the lime was much lower than expected, and the orange was much higher than expected. Okay, so it appears the lime flavor is less likely than expected, and the orange flavor is more likely than expected. Okay. Now, some years on the test, students will literally go through and say every one of these. That's not what the informal follow-up is about. Okay, the informal follow-up is what caused you to get a small p-value, right? The grape didn't cause a small p-value, right? It was pretty much in line. That is not what triggered the rejection of the null hypothesis. So you should be mentioning the categories that are basically contributing the most to the size of the chi-square, right? The larger the chi-square, the smaller the p-value. So the ones that have the largest contributions, those are the ones that triggered us to reject the null hypothesis. So those are the ones you mention in your informal follow-up. Okay, back to question 12 here. My observed for brown, find my brown, there we go. Brown, I had 61 of those. For yellow, 109. Okay, for red, this one was pretty low, 49. And no, I didn't eat all the reds, if you were wondering. Blue, 67. Okay, for green, I had a lot, 175. Yeah, and that was supposed to only be 10%. And for orange, I also had a lot, 167. So you can see, since I used the wrong kind of M&Ms, clearly we're off. But that's okay. Maybe I should change it to, do plain M&Ms follow the same distribution as peanut? That's what we'll do. So my null hypothesis is, do plain M&Ms follow the peanut distribution of what we have there. Okay, now I feel better about the problem we're doing. All right, so step one, I got to get those counts into my calculator. Okay, and now I got to find the sum of that. So 628 is my sum. And I have 4 categories that are supposed to be 20% of that, right? So that's 125.6. Okay, and then these are supposed to be 10%. Okay, so that's how you handle a non-uniform claimed distribution, right? Just work it out, find your total, and the expected counts can be fractional. That's okay. Observed counts can't, but expected counts can. All right, for our chi-square check, all expected counts are at least 1, and 0% are less than 5. So a chi-square goodness of fit test should be safe. All right, now for our work. Our chi-square is going to be observed minus expected over expected plus the next one. And all the way out to our last, and this one is 167 minus 62.8 squared over 62.8. So you can see, yeah, we're going to get a small p-value here. Oh, okay, so 125.6. Okay, and entering. Since I know we're getting a small p-value, I'm going to just jump straight to do it this way, as opposed to the goodness of fit test, because it won't tell me which category has the largest contribution. All right, so list 1 minus list 2 squared divided by list 2. And wow, look at those. Yeah. Sum of list 3. That is massive. And my degree of freedom is 1, 2, 3, 4, 5. Okay. And of course, if you're using your table, that's just going to be way off the side of the table, so you know it's less than whatever the smallest entry is, which is actually 0.0005. If you want a more accurate p-value, that's where you can use your goodness of fit test. Degree of freedom is 5. Yeah, look at that. It just says 0. That means it's so small the calculator rounds it to 0. So p-value approximately 0. All right, so we get to conclude that plain M&Ms do not follow the peanut M&M distribution, right? With p-value of approximately 0, we have very strong evidence that the distribution of plane M&Ms does not follow the claimed distribution of peanut M&Ms. Okay, now for the informal follow-up, that's where I want to look at list 3. Yeah, those last two categories are just huge. I mean, they're all off, except for, look at that, the yellow. The yellow is not that far off. All of them are pretty darn far off, but holy cow, the green and the orange are way more than expected. Okay, so the green and orange colors are much more likely than 10%. Okay. And there we go. That was fun. Okay, on to our last problem. All right, a wheel of fortune at a carnival is divided into 4 equal parts. Okay, so in theory, if it's weighted evenly, it should be equally likely, each a quarter. You suspect the wheel is unbalanced. Not all parts of the wheel are equally likely to be landed upon when the wheel is spun. You sit there and watch 500 spins. Yay, fun for you. The results of 500 spins are as follows. Perform a goodness of fit test. Is there evidence that the wheel is not in balance? By the way, not that long ago, but before your time, some people went to casinos and they literally sat for days watching roulette wheels, keeping track of the results on the wheels. And every once in a while, they'd find a wheel that was out of balance. And then they would go bet and make a bunch of money. Now casinos also keep track of the results of their wheels, so they will catch once a wheel is out of balance, and they'll put it out of commission, rebalance it, replace it, whatever. So, darn, can't do that anymore unless you find some really backward casinos somewhere. Okay, so let's do this. Null hypothesis. All categories. Is that what it is? A category? Or all parts. Are equally likely. Alternative. Not all parts are equally likely. Okay, so we've got observed and expected. So part 1, 95, part 2, 105, part 3 got 135, and part 4 got 165. Okay. Again, we're going to just enter these in the calculator. Oh, they did tell me that it equals 500, so this would be 500 over 4, right? Or 125. Okay, so our check, all expected counts are at least 1 and 0% are less than 5. Notice if one of these had been less than 5, we would fail, right? Because this is 25% if one of them fails, right? Once you have up to 5 categories, now you can stomach one of them being between 1 and 5, right? Because that would be the 20%. So anyway, all expected counts are at least 1 and 0% are less than 5, so it is safe to proceed with a chi-squared goodness of fit test. Yay! All right, so getting our chi-square. Observed minus expected, squared over expected. And continue. I'm just going to write them all this time. There's only 4 of them. There we go. Right, and let's see, list 1 minus list 2 squared divided by list 2. $24. And our degree of freedom is 3, right? Because we had 4 categories there. So let's get our p-value. By the way, some of you, let's look at the table again, because some of you don't have that GOF on your calculator. So degree of freedom of 3, 24. Again, we're off the table, so my p-value is less than 0.0005. Okay. To get the accurate one. And there we go, 2.5 times 10 to the negative 5th. Okay, so very small p-value. In other words, very strong evidence that this wheel is out of balance, maybe intentionally. Carnivals are kind of somewhat known for doing that type of thing. All right. Oh, then again, the carnival probably could say, we never claimed it was in balance, right? All right, with a p-value of 2.5 times 10 to the negative 5, we have very strong evidence to conclude the wheel is not balanced. Okay, now for our follow-up. It looks like part 1, well, let's look at the lists here. Part 1 was quite a bit less likely to occur than expected, and part 4 occurred much more often than would be anticipated. So part 1 was observed less than expected, and part 4 was observed much more often than expected. And there you go. That's how you do the chi-square goodness of fit test. And again, don't forget the informal follow-up. Thanks, and have a good day.